All right, hello everyone. So welcome to our talk from Esperanto Technology, accelerating AI and non-AI workloads with 1,000 plus RISC-V energy-efficient cores on a single chip. Now, I think many of you have heard of Esperanto before, and we've been a founding member of the RISC-V group, and we've been involved since the beginning, so we know many of you here in the audience. I do want to thank our employees and investors before I get into the presentation. It's with their hard work and dedication that we've gotten to this point of having functional silicon. I'd also like to thank some key partners. We can't name all our partners in the industry for confidentiality reasons, but I would particularly like to thank Synopsys, who provided all of our EDA tools, support, emulation boxes, and so on. We had great support from TSMC on their 7-nanometer foundry to get wafers on a super hot lot basis. Great support from Amkor for assembly and substrates and the like, again on expedited basis. Allchip, a key partner for the back end. And then also people from the RISC-V community. So a few of you are out here in the audience. I'd particularly like to give a shout out to Roger Esparza, who played a key role in the design of our first chip. And Roger is currently, well, you may know him as the longtime co-chair of the Vector Committee for RISC-V, and then also CEO of Semidynamics. So thank you, Roger. Thank you, other partners. So let me jump in. We actually see ourselves as a foundational RISC-V company. So with RISC-V from the beginning, we brought together a group of very seasoned CPU designers, architects, software people, and so on. Melded in some AI capabilities over time, and really I would say the average level of experience is decades, not years, but decades on the team. These are really seasoned people. We have designers and architects from, as you might imagine, Intel, NVIDIA, ARM, MIPS, Spark. We also have Cell people on the team. And we have many great software people who've joined us as well in the machine learning and AI area. Now, you might not know, but our founder, Dave Ditzel, was really seminal in the whole formation of the RISC-V and the RISC industry in general. Dave was co-author of a famous paper back in 1980 with another famous Dave, that's Dave Patterson of Berkeley, who was, of course, the progenitor of RISC-V. They wrote the seminal paper, A Case for Reduced Instruction Set Computing in 1980, which really triggered the RISC race. So you might say we might have been in it from the very beginning, in a manner of speaking. Now I'm delighted to say that we now have silicon-proven RISC-V technology. We got our first silicon back earlier this year, and I'll give you some of the results that we've seen so far. Our strategy is to serve from cloud to edge, a very big dream, but we think our technology using RISC-V is highly scalable, and you'll see why in just a few slides. So our market entry point is for data center inferencing in hyperscale data centers, but we really believe the technology has the ability to scale towards the edge into near edge and fog applications. And finally, our real focus is on power efficiency. So not only delivering the best performance possible, but the best performance within a constrained energy environment. And that's a real key focus for our team. Again, supported by tier 1 investors, major hyperscalers, and enterprise and SoC companies. So you may have seen this slide before from the Hot Chips presentation, where Dave Ditzel presented kind of the early disclosures on our ET SoC1 chip. It is a 7-nanometer chip manufactured at TSMC, 24 billion transistors. There's a die plot on the right. You can kind of see it's a very regular design made up of CPU clusters that we call shires. Each of those shires, each of those blue squares, has 32 cores, and if you do the multiplication, that comes out to 1,088 so-called ET minion cores, all operating together on a single device. Each of those is multi-threaded and actually has a vector and tensor unit that attached to it that Roger Esparza was influential in helping us create. Also on board are 4 big out-of-order cores for running Linux. These are our so-called ET Maxion cores. These are 64-bit cores, which are designed for self-hosting applications. Many times early on, you'll see us sitting in a data center as an accelerator, sitting next to a Xeon, for instance, in a server. But going forward, this same technology can be used in self-hosted applications for the edge, where you'll be wanting to run Linux on board the chip. Lots of memory on board, 160 megabytes of SRAM, and up to 32 gigabytes of external DRAM per chip. And of course, the usual things like root of trust and so on. But the most important thing to focus on, I think, is the power number. The typical power budget that we have for this chip is 20 watts. So that's running 1,000 plus RISC-V cores at 20 watts. And it's a completely different design philosophy than most competitors in the industry have taken. And we'll share more about that in just a moment. Status-wise, we've got it in the lab, and we're going to share some results with you. So first of all, every parent is proud of their child. Everyone says, isn't that child wonderful? Well, we're really proud of our baby here. I think some of you in the room may remember a presentation by a famous chip designer, Pete Bannon, at that time of Alpha Group of DEC, now more recently at Tesla. Pete went to a microprocessor forum presentation, and he just stood for the first 30 seconds or so and looked at the beautiful die plot of the Alpha, I think it was the EV6 chip, and he said, isn't she great? And I just thought that was a perfect example of how a designer feels. So that's a real wafer in our lab. That's a 7-nanometer chip. You can see it's a relatively big chip, not gigantic, but relatively big. Top center is that chip on a PCIe card running machine learning software. And then we're mounting those PCIe cards into high-end servers, in this case from Supermicro. And then you can see a rack of Supermicro servers on the side there. That's how we provide cloud access, initial cloud access to our software development team and also customers. We'll ultimately put that cloud access in a colo, but for now it's in our engineering lab. And what I can say is we're beyond hello world now. We're at hello customers. So it's been a lot of progress since we got silicon back. We have real machine learning workloads running on all 1,000 plus ET Minion cores. And again, those are 64-bit proprietary cores of our own design. We're doing continuous integration testing now. We're expanding continuously the support of machine learning operators and additional models. And we're actually planning to offer support for just generalized, highly parallelizable workloads as well. So think traditional HPC kinds of applications. ET Maxion is running Linux. It booted at 1.5 gigahertz, which was the typical design target, so great, fantastic. PCIe Gen 4 and LPDDR4 up and running at speed. We did our first public disclosures of performance with Samsung at their Samsung Tech Day event a couple weeks ago, where they showcased what could be done in an edge application. Again, keep in mind that we see this technology is very scalable for the edge, but an edge application for smart SSD. And we'll talk more about that in just a moment. So we're preparing the cloud access for our customers now. And of course, we're replicating all the benchmarks that we talked about when we were in emulation mode. Last bullet at the bottom, early access programs are underway. So we have customers who are entering into our early access program. If someone is interested in that, please contact us directly, or you can get information at chips@esperanto.ai. Let me turn back to Synopsys for a moment, and again, thank them for their contributions. For more than a year, we ran software on the big Synopsys ZeBu boxes. So you really can get a picture of what the chip is going to do. And I think it was largely due to Synopsys' help and work that we achieved first pass functionality on this chip. Because we knew it was going to work. We'd already been running the software for months and months and months and months. So anyway, I think it's a real tribute to that kind of co-design aspects. Just a reminder, we set out to optimize our chip for the requirements and challenges, particularly of recommendation workloads in the data center. We had a key partner who helped us identify the needs of that workload and a data center customer. This was a hyperscaler who actually had key influence on us in the design of our first chip. Now, what they, of course, demand is a lot of performance. 100 tops to 1,000 tops on a card. Very importantly, air cooling. So that actually limits how much computing you can put on a card, typically 75 to 120 watts. Multiple data types, int8, FP16, FP32. Lots of memory to hold the on-chip models, both on-chip memory and also access to DRAM. So at least 100 gigabytes of memory capacity per chip and 100 megabytes or more of on-die memory. And a key requirement is for both sparse and dense computing applications. Finally, it has to be programmable. What's the death knell for many AI chips in the past? Well, they're difficult to program. This is a traditional HPC programming methodology that people are familiar with and can identify with. So being highly programmable is a protection against future evolution of machine learning models. Now, again, you may have seen this slide from Dave, our founder, but what it's trying to do is point out a vastly different approach to this kind of chip development. So typically you might find from a machine learning or CPU company a giant hot chip that burns something on the order of 250 watts, and it has a limited number of CPU cores on board. And the idea is you just maximize absolutely what you can get out of that single chip. What we found to be a better approach was to limit the power consumption of individual chips such that you could put 6 or more on a single board and stay within the power limits of that board at, say, 120 watts. So then that allows you to, for instance, have 6 times 1,000 plus cores on a single card. So think about 6,000 multi-threaded cores all in a power budget that fits on a PCIe card. So the computing power is really quite immense. Now, how do you do that? Well, of course, some clever design tricks are required. It's not as simple as just throwing down 1,000 off-the-shelf RISC-V cores. These are custom cores with all sorts of low-voltage design techniques built into them, and I'll share some of the details in just a minute. But the whole key is a different philosophy, thinking about the problem differently. It's system-level performance, not chip-level performance, and that's what we're delivering, all within an energy footprint of something that can be air-cooled. Now, this slide's kind of interesting. It's a study that I want to share with you that we did initially on the development of the chip. If we took just 1,000 plus RISC-V cores and ran them at full speed, like everybody else, we would have 1,000 cores at 0.9 volts, which would be 275 watts. So obviously that's not an implementation that would work. Well, you could scale down the voltage, operate at a lower operating voltage, and you might have a 100 plus watt chip. But what we found is if you scaled all the way down to a 0.3 watts or so of operating voltage, you could have a very compelling chip operating at a very low wattage, but from a systems perspective, it might not deliver the absolute best performance. So what we tried to do was find the sweet spot where we deliver the best performance on a multi-chip card with the best energy efficiency. And basically what you can see is, substantially better machine learning performance than what you would otherwise have. And hugely better energy efficiency versus just this fast, hot chip kind of approach. So that kind of set the design goals for us. And then we set out to architect the chip accordingly. So starting with the key computing element, which is the so-called ET minion, that's an energy-efficient RISC-V 64-bit core, proprietary. And on the right side of the screen, you see kind of a block diagram, so to speak, but it's relatively to scale. So the RISC-V integer pipeline is actually a small piece of our so-called minion processor. The bigger pieces are in the vector and tensor accelerators, and also the fact that we've optimized those vector tensor accelerators and extended the instruction set of RISC-V for our purposes. Things to point out here. So it's a 512-bit wide integer pipe, 128 integer ops per cycle, 256-bit wide floating point pipe, and multi-cycle instructions. Talking about the vector and tensor instructions, which some of you may like, I know there's another presentation coming up, or maybe it's already been done on RVV vector spec. But these vector and tensor instructions, particularly the tensor ones, are really, really valuable to us in machine learning applications where you can run hundreds and thousands of cycles on a single command. Now, we put 8 of those so-called minions together to form a neighborhood. The neighborhoods are really designed to work closely together. The minions share an instruction set cache, an instruction cache, so that they're basically operating on the same code. This is typical of a machine learning algorithm. And then we've added instructions to make cooperation between the minions more efficient. Now it starts to get really interesting. We put 4 of those neighborhoods together to make a 32 CPU cluster that we call a shire, or a minion shire. And here's where many of the really clever tricks come in. You'll see that on the right side in that diagram, you'll notice that the 8-core neighborhoods are all in a low voltage domain. And then the NoC, the on-chip mesh, is also in a low voltage domain. And then in the center for memory, there's nominal voltage, so for the instruction caches and so on. And so by having multiple power domains and optimizing the different sections of the chip, we're able to really achieve low power requirements. And you'll see how this all comes together in a moment. Here's what the whole thing looks like. So on board, 1088 RISC-V minion shires. On the sides, you'll notice there are 8 so-called memory shires. These are the interfaces to the LPDDR4. In the top right, you'll notice one so-called Maxion and I/O shire, where we have 4 of those high-performance, out-of-order Maxion cores on board, service processor and the like, and then PCI providing the PCIe Gen 4 interfaces. Again, lots of memory and so on the chip. Now notice again the very regular design. It's basically a 6x6 array. So what we can do for edge applications, it's very easy for us, one, to test on the existing silicon just how much performance is required for a given edge application. Then it's very easy to do a derivative chip by just scaling down, for instance, the number of so-called shires. Likewise, scaling up is also easy because of the regular nature of the design. And I do want to let you know that we have already engaged with our first strategic partner for IP licensing. We have concluded our first IP licensing arrangement for a company, international company that's pursuing edge chip applications. So this strategy is very much real, and we're in talks with others about those same kind of edge applications and potential joint developments. I think probably most of you are not going to dwell on the vector tensor extensions, but we added our own extensions. We worked very closely with the RVV committee. At the time, we felt in this design that, one, that spec wasn't quite ready, but secondly, this is a much more energy efficient and less overhead design than the current RVV spec. So we still think we made the right choice to go our own way here, and this is pretty much hidden from our customers because of how the software framework that we use, which I'll share with you in just a moment. In the future, we may embrace the RVV spec for particularly tying it to our Maxion processors, but again, right now, each of those 1088 minion cores is tied to a vector and tensor accelerator, and that's, again, if you think about the power requirements there, you have to be very, very careful not to include extra overhead or you'll blow the power budget. Software development, we leverage heavily the work of the RISC-V community, so thank you for software developers here. Of course, RISC-V provides some of the basic tools and debuggers and so on. But for us in the initial implementation, where we're targeting inferencing and data center, we leverage 2 other open source projects, namely the GLOW framework, which was an open source project launched by Facebook, standing for graph lowering compilers. So that GLOW framework ties to PyTorch environments, so that's a very clean, nice way to interface with our chip. And then in the case of TVM, that's a way of interfacing direct native to TensorFlow. Both frameworks or both compilers, of course, can also interface through the ONNX Open Neural Network Exchange format. So basically, we can support other frameworks, Cafe2 or the like. And our job has been to really optimize the device-specific versions. And our system software. All right, so let me just quickly share with you a edge use case. Again, our market entry point is in the data center, but the goal is to span from data center all the way to edge, or cloud to edge, as we say. So this is an excerpt from our presentation with Samsung, where we together did a technical feasibility study of using AI to accelerate smart SSD. So in other words, improving the performance and bandwidth of SSD by adding AI capabilities to it. Now the problem is, in the data center, parameter size for these models is growing very rapidly. And particularly in recommendation models are generally about 70 to 80% of the workloads in a hyperscale data center today. If you think like someone like a Facebook or someone like that, that dominates their inferencing in the data center. But the models are getting larger and larger, so it's really kind of a exponential growth. So what do? Well, these models typically require giant embedding tables. And the idea is that this is a way of sort of doing a lookup to quickly assess connections between people or things and so on. But the embedded table calculations are very deep. They're very memory intensive, but not compute intensive. So what you can do, and this is what we did with Samsung, is do a feasibility study to put the embedding tables directly together with the AI capability of a chip like Esperanto. And basically then that frees the CPU and RAM, and it really improves the accuracy and bandwidth. And I'll just jump to the conclusion because of time. But you can see this presentation online. What the results were that we yielded a 10x to 100x improvement in the CPU to SSD bandwidth by applying these AI techniques in the SSD. And so this is just an example of what could be done from a joint development or a licensing perspective to embed this technology in another chip. So in summary, we're very proud of what we've achieved. Thanks to our partners, we have first pass functionality. Thanks to TSMC and Amkor for their capacity allocations and speedy time through the fab. We got the chips in the lab, they're up and running. They're now beyond the hello world point, and we're now beginning to engage with customers. So it's a highly scalable design. If there's a chip developer in the audience that thinks they might want to be a joint development partner, please contact us as well. And with that, just a reminder, early access program has begun. So if you're interested in evaluating those chips and are a qualified customer, please let us know. And that's it. Thank you. Questions?
Any questions within the room?
Okay, I guess it's a wrap. Thank you, everyone.